Good morning, guys. This is supposed to be the demonstration on electricity. There's going to be a few starts and stops as I build the models and display each one. So the first one I have is just a simple circuit. I want to talk to you about conductivity versus resistivity versus what's a current doing. So I want to go over like the basics of electrodynamics, and I want to introduce some circuit elements to you. And I've got a card. Be helpful if while you're watching this video, get out that schematics handout with all the symbols on it, because I'm going to show you what the real world equivalent of some of those symbols are. Now my motor and my light bulb, I just tested those on this kit. They're burnt out, but I do have the Snap Circuits kit, so this kit's a little bit older, a little bit more rustic too. You can tell by the rig that I've built here. So getting into the components, this of course is the battery. You guys might recognize that as a size C Duracell battery. I believe it supplies 1.5 volts if I'm correct, and that's under the black tape right now. So I can't verify that information, but what that is 1.5 volts of push on the electrons. So all the electrons that it's pushing them at 1.5 volts. So our maximum current, if we have no resistance, which is impossible, our maximum current would be 1.5 amps. Generated by that battery, but there's no way to build a circuit without at least a little bit of resistance, unless you're talking about superconductors, and we don't have the rig for a superconductor here. So the next, and then there's just plain wire. Wire, if you haven't figured it out, is just a straight line, okay? And then this over here, this is called a knife switch, and the knife switch basically works. It's what the mad scientists used to use. And you guys might be able to see this over here if I get a good connection. There's the good connection. Can you see this element over here? This is a diode. This happens to be a red diode. Facing back to the camera, it gets incrementally brighter. So you can see as soon as I connected the switch, that is, I closed the switch, I closed the circuit, and if we've got good contact, electricity flows through the diode and it emits red light as it flows through the diode. Now we'll be talking about the structure of diodes later, but this is an LED. So as it passes through there, the electrons do give off about 2 electron volts of energy as they pass from one semiconductor to the other, and that is the equivalent of a red light photon. That's why we see red coming out of this diode, okay? And then the electrons continue on through the white wire and back to the battery. So what do we need for electricity to flow? Well, we need a voltage. We need a source of push for the electrons. Electrons have to be pushed or pulled through massive summative or cumulative Coulomb forces. The battery supplies that by means of a chemical reaction. It's running, there's a chemical reaction going on between the acid in the battery, the cathode of the battery, and the anode of the battery. All of those made of different materials, usually 2 different types of metal for the cathode and the anode, and then the acid also is a mix of acid and a salt of one of the metals. And the stronger the acid, the more fast the reaction goes, the more voltage you get out of that. The 2 metals swap electrons, and in the swapping of the electrons, we're actually pushing electrons through the wires. Now, you need voltage, you need a circuit or a circular path for the electrons of conductor, for the electrons to travel on, and then you need a source of electrons. Well, the electrons are coming from the battery, but they're also coming from the wires. Okay? All of this is matter, and therefore it's composed of atoms, and therefore it has orbital electrons around its atoms and molecules. We know that copper is a good conductor, and what does that mean? Principally, that means it responds very well when you apply voltage to it. That is, when you push on electrons in copper, they tend to move fairly easily. That's essentially what conduction means. You see, I've got a popsicle stick here, so we're passing everything through copper right now. Let me, real quick here, I'm going to disconnect from the diode. Got a little alligator clip there. And then I'm going to connect to the popsicle stick. And then I'm going to connect to the diode, and it should light up, right? Can you guys see through my fat fingers? Is it lighting up? No, it's not lighting up. The popsicle stick is made out of wood. Yeah, it's made out of pine, essentially. And wood is a very poor conductor of electricity. It's got a high resistance. If you deposit extra electrons on wood, they basically just get stuck right there and they can't flow through the wood. The wood is extremely high in its resistive property. Now, why don't we use wood as the surrounding for our wires? Well, it's not very malleable. It's rather rigid. So wood, and it's not very heat resistant. It tends to combust when you expose it even to a minimal amount of heat. It starts to combust. So electric fires are not ideal. We want to practice safe electricity, so we need an insulator, and that's what all these wires are wrapped with, is plastic. Plastic is a malleable, moldable insulator that we can wrap the wires in, and then I can safely touch the wires without fear of shocking myself. Now, if I only make one contact to the circuit to break it and just touch one alligator clip, then I'm not going to receive an electric shock. But if I try to touch two alligator clips at the same time, then my body becomes part of the circuit and I receive the voltage of the battery. If we're pushing enough amps, I could risk stopping my heart right there. I don't think we're pushing enough amps in order to stop my heart with this experiment. I think we got too much resistance in the steel alligator clips to yield that kind of amperage. So our diode is glowing. That means electricity is flowing. The second element is the knife switch. And a switch is just basically a conductor that can close or open. So this is a switch in the open state, and you notice the diode's not giving off red light anymore. That's because electrons are not flowing. I have opened, what have I opened? The circular pathway, or the circuit. The circular pathway of conductive material upon which the electrons are traveling. As soon as I close that circular pathway again, or close the switch, then again electrons start flowing again, and that's evidenced by the glow of the red diode here, the light emitting diode. Okay, so we proved, we've gone over what a battery is. A battery is basically a cylinder that's contained a chemical reaction between an acid and two metals, and that chemical reaction allows for the escape of extra electrons from that chemical reaction. We take advantage of that by passing the electrons through conductive wire, through a switch, which we can choose to open or close. If the switch is closed, the circuit is complete, and we should expect electrons to flow. If the circuit's open, the circuit is incomplete, and we've taken away one of the three things we need. We need voltage, source of electrons, and a closed loop, okay, or a circuit. By opening the switch, we take away the closed loop. The loop is not closed anymore. There's a gap in it right here, right under the switch, okay? The switch acts as a bridge across that gap, and when that bridge is covered by the metal switch, then electrons flow across the switch and light up the diode. Okay, so we've got some other materials besides wood. So I'm going to do the similar experiment now. I'm going to leave the switch closed. Well, actually for safety, I should do that. And what I have here is a gum wrapper. Okay, little crushed, unused gum wrapper. It's a piece of aluminum foil, essentially. Okay, a little bit of aluminum foil. So we know aluminum is a metal. And I'm going to leave that open there. I'm going to reclose my switch. So aluminum, it's a metal. Is it going to conduct or not? We know that the wood didn't conduct. What about metals? Are metals fair conductors? Well, this one isn't. That's surprising. I got my knife switch. Knife switch is in good shape. Oh, there it goes. I just got to press down hard. Right, see that? So I'm actually passing the electricity through the foil of the gum wrapper. So the aluminum is serving as a contact and a conductive pathway intermittently as the pressure varies, I guess, between my finger and the aluminum foil. So if I push the diode contact into the aluminum foil and make a good contact, then indeed electrons are flowing through the aluminum foil to conduct the electricity. So we have a poor conductor and a good conductor. Okay, and then here we have a different device. So I'm going to unhook my diode for a second, and I'm going to bring my pen in. Now I want you guys to see what I have here. What I've got is a galvanized steel nail, and it's been wound with loops of copper with no insulator around them. Okay, so it's just raw copper wire. Okay, in a coil, and it looks like from this direction that's a clockwise coil around the wire. I'm going to hook this up to the two leads. This thing should start getting warm in my hands. Yep, all ready. And now I want to touch to the pin. Is that going to work? Not working. That must be chrominated. Not working. Do I have? Yeah, it might be steel there. Huh. Maybe I don't have a good connection. It's not getting hot yet, so chances are I don't have a good connection here. Or maybe just not enough voltage. I tell you what, I'm going to remove the switch. Remove alligator clips from the battery. And let's do a direct link to the battery so we are not losing conductivity. We're creating good conductivity, and then, come on, oh, let's move that down closer to the tip. That nail's starting to heat up a little bit, yeah. Oh, bad conductivity. Get under that right there, push, and come on. Oh, it's not going to do it. Maybe my battery's too weak. Battery might be too weak. Oh, maybe a little bit there. Yep, it's starting. Yeah, you guys, I'm not sure if you can see that. So what I have is copper looped around a steel nail attached to a battery, and what I'm getting is magnetic force. There we go. Come on. If I can get right down the throat, maybe I can contact both of them and pick it up. I'm getting a weak magnetic force out of, there we go. See how I was able to stand that up? Weak magnetic force out of the nail. Why am I getting a magnetic force out of the nail? Does it have something to do with the copper coil and the battery? Well, reading ahead in Bouchon, you might be able to guess that the answer is yes. Yeah, that battery must be near dead because that didn't get hot at all. Usually, this is an electromagnet. You can make one, especially if you have kids. I would take the effort to make one of these, play around with it with some paper clips perhaps, and make sure you have a fresh battery, not one near dead like I'm using. And you will get, if you put a chunk of iron in the middle of a copper coil and then you conduct electricity through the copper coil, you will get a magnetic field or magnetizing of that copper, the steel or the iron embedded in the middle of the coil. That's how you build an electromagnet. Okay, so I'm going to pause here. I do want to review. Hope you guys can see that. So we covered in this demonstration the knife switch, or the switch, and that's the symbol for the switch. We covered the wire, which is just a simple conductor. So if you see a straight line in the schematic with no indicator on it, you just assume that that's copper wire. We've covered a battery, and a battery can have a different number of, these are called the cells of the battery, where you get a fat line, then a short line, then a fat line, then a short line. The fat line is the anode, the short line is the cathode, and you can have multiple cells to a battery. So the more cells you stack in a battery, the stronger it gets. This would be like a car battery. That would be like a 12 volt. A battery can be just one big line, one short line, and that's it. Or it can be expandable to multiple cells, depending upon whether you're talking to an engineer or not, and whether that detail matters. Typically it does. Typically the voltage supplied on a circuit does matter. The motor we didn't get to because the motor in this kit is burnt out. And the light bulb we didn't get to. A light bulb it's a circle with a little curly line in the middle of it, and that's a filament line. So it basically looks like a pictogram of a conventional light bulb. That's not the same as a diode. I'll show you the symbol for a diode here in just a little bit. Okay, so let me pause and set up the Snap Circuits kit. Alright guys, I'm back for the series circuit demonstration. This is on the Snap Circuits. So I'm going to hold this up real quick. Show you guys that I've got I got a battery. I've got two this time. So these are double A's, each rated at about 1.5 volts. So, and they're wired in series. Okay, so that means that there's a single contact here. We've got negative to positive, and then a metal plate here on this side of the cell to connect the positive of this battery to the negative of this one, and then positive out here. So in effect what we have is negative coming out this way, and there's a little white wire underneath that connects to this terminal here, and then positive coming out this way, connecting to this terminal. So this is, you would call, of this battery cell, this 2-cell battery, you would have, this would be the positive terminal, which Michael Faraday would say the point in the circuit where the positive charge tends to gather, that's the anode. So this is the anode of the battery here, effectively, and then this is the cathode of the battery here. So we should expect the electrons to start their journey this way around the loop, terminating here, but according to Ben Franklin, that knucklehead, the flow of positive charge would be in the opposite direction from the electron flow. So current is actually coming around this way. So on this side of the circuit, I would, if I'm drawing a vector to describe the flow of current, it's this way. And if the voltage vector always matches the current vector, so the voltage is also this way. Okay, remember, current is the flow of positive charge, and then every other vector makes sense from there. Resistance isn't a vector, it's a scalar. Okay, so I do have a switch here. We covered the switch, and you notice here the battery, I'm not sure if you can see the red paint there on that plastic, but that's the symbol for a battery. And then I've got the symbol for a switch here, right at the switch. I really love these Snap Circuit toys. That's the symbol for a line. And then this one just says L1. Well, that's a light bulb there. Okay. So it doesn't match the schematic symbols there at the light bulb, but it does. It's got a circle with an L to indicate that it's a light bulb. If I turn the switch on, boom, we get electric light. Now, let's talk about the reason that's happening. The reason that's happening is because as soon as I close the circuit, then we have all three conditions necessary for electricity. We have a we have a voltage, 3 volts on this circuit, because 1.5 plus 1.5 is 3. Okay, it is in series orientation, so the current is constant. So whatever current we're manifesting here is the same that we're manifesting here. And I've got a multimeter. I'm about to take some measurements of the current on the DC circuit. I'm also going to take some measurements of the voltage at different points as well. In order to take a measurement of the voltage, I'll have to break the circuit, probably at the switch, in order to measure the voltage, okay? Because otherwise I'll create a parallel circuit with my meter, and that will not do, okay? So I'll break the circuit here, measure the voltage, and then I'll reconnect that one, break the circuit here, and measure the voltage, okay? So let me turn that off and get set up for the first voltage measurement. Now, in a series circuit, follow along in Buchon or possibly your notes from the PowerPoint. What do we expect to be constant in series? Do we expect current to be constant in series or voltage to be constant in series? Does anyone remember? Does anyone look at their notes or look at the PowerPoint? Remember that? And I can tell you the answer in 3, 2, 1. You're going to expect current to be constant in series. So my initial measurement of voltage here, let me see if I can connect these. And I know you guys can't read the multimeter here, but I am getting an initial reading of, looks like 3 volts coming off the battery. Right at 3 volts. Good. So I can reconnect there. Now I'm going to connect the circuit and let the voltage run through the light bulb and then measure the voltage on the other side of the light bulb. So let me get this, turn that off, let me get that reconnected. Okay, so I had 3 volts coming off the battery. In between the battery and this contact here, 3 volts available. But now the light bulb's going to offer some resistance. It's effectively resistor number 1 on this circuit. So as the push of the electron tries to get across the light bulb, it's going to meet some resistance, and we might see the voltage drop a little bit after the light bulb. So let's turn that on, and again, contact. Oh, got to reverse the polarity. Come on now. Do we have good contact? Well, the light bulb's not lighting up, but I am getting a reading. It's still 3 volts of potential, but why is the light bulb not lighting up? Doesn't make any sense. That's weird. I'm not making a contact. Yeah, I'm making a contact across the light bulb. The voltage should have dropped, but it's essentially the same. But now the light bulb, it's telling me that electricity's flowing through my meter, but the light bulb's not lighting up. That is odd. That is just strange. But it doesn't light up going there. But there's a voltage, and again 3 volts, but without the light bulb lighting up, I wouldn't expect the voltage to drop. So now the mystery is, why the heck is the light bulb not lighting up? There should be no effective difference between my nodes, or my points here, and let's see what that is. Okay, now that's an effective voltage of 0. So it means maybe my meter is offering too much resistance to get a good measurement. And then the last one I wanted to do was this contact over here. So let me break this contact. Let's see, what is my voltage? That's reverse polarity. That voltage is also 3 volts. So 3 volts of potential. Okay. Yeah, don't understand. Let's see if that. Okay, negative polarity. Let's try this. When I connect that, does that dim the light at all? No. Okay, now I'm getting a reading, and it's just under 3 volts of polarity. So the light bulb is offering some resistance, and the resistance is manifest as a drop in voltage across the line. So the voltage here is exactly 3. The voltage here is like 2.8 across the light bulb. Okay, so we did experience a voltage drop. Now, one more thing I want to do, and I think I'm going to pause the video. I'm going to add another resistor in series. I've got another build here. Yeah, fantastic. So immediately what you can see when I turn this thing on, you can see that one light bulb is a little bit brighter than the other light bulb. This one I would describe as dim. It's almost got an orange quality to it. And then this one is the one from the first build. That doesn't look as bright as it did before, does it? So what I've done by adding the second light bulb is I've increased the resistance on the circuit. So we know we're supplied with 3 volts here. Let's go across this one. And now the first light bulb is only reporting a voltage of 1.5. The second light bulb, 1.5. So it seems like both light bulbs are splitting the voltage, or splitting the force. And that effectively makes sense, because you're pushing the electrons through resistance. Well, when you do that, you lose some of that potential energy, and that potential energy is no longer available. So if I'm supplying 3 volts, but I consume 1.5 volts of push at the first resistor, then I only have 1.5 volts left to push through the second resistor, or the second light bulb. Okay? So we get a different result with 2 light bulbs, and we see that actually the voltage is distributed. Now if I make contact here and here, I'm going to get 3. Let's go this way. Well, the meter's not. Let me check that off. Make contact here and here. Yeah, I get 3. Right? But if I connect the circuit and measure it across each of the light bulbs, I only get 1.5. And that goes along. If you look in chapter 4, Buchang will tell you that voltage is cumulative across the resistors in a series circuit. But we should find that, what was the key that I wanted you to remember about series circuit? Its current is constant. So now I'm going to change my multimeter to measure the current, and I want to go to 10 total. And now I need to see what's the current here. That's negative polarity, so I got to switch. Okay, what is the current? That is off the scale. It doesn't look right. Oh. I got to measure the current. Got to measure the current. I can't measure the current across the light bulbs because that creates a parallel circuit. I have to measure the current like this. Break the circuit, measure. And that is off. Let's go to 250. So I'm more than 10 milliamps here. I am, oh look, electricity is flowing, and I am, if that's on the 250 milliamp scale, I'm at 125 milliamps. Okay, so this is enough to stop my heart if I'm not careful. This is twice as much as what's necessary to stop my heart. Okay, so I don't need to be messing around with this stuff. Okay, I definitely don't need to try to insert my own pacemaker or put these probes into my chest or whatever. This is more than enough amperage to stop my heart. 125 milliamps here. Okay, now I've broken that connection. Let's put that back together, and now let's destroy the connection between the two light bulbs, and now let's establish that with a probe. And what number am I going to get if current's constant in series? I should get 125 again. 125 milliamps. Doesn't matter where I measure on the circuit. Okay, break this one, put my posts across, measure 125. Okay, and then last one here, posts across, measure 125 milliamps. Okay, I'm sorry you can't see the reading on the meter. You'll just have to take my word for it. But 4 different measurements across the series circuit. So from here to here, the total current was 125 milliamps. From here to there, 125 milliamps. From here to there, 125 milliamps. 125 milliamps. All 4 measurements. Does that make sense? All right, now remember the PowerPoint. What did the PowerPoint say? The PowerPoint said that the current in series is like a 1-lane road. Okay? You can only go and what is current measuring? It's measuring the flow of electrons. So does it make sense that on a 1-lane road, the speed of all the cars are only as fast as what? Well, that would be the slowest car. Okay? So the slowest car on a 1-lane road determines the speed for all the cars. So there's I wouldn't say just one electron, but there's probably several million electrons that are just going through slow because they're feeling a whole lot of resistance at the light bulbs. And because they go slow in those areas, there's only one pathway. All the electrons behind them are kind of bottlenecked, and you get a traffic jam, and everyone crawls along at the same speed. Okay? So it does make sense that the speed we measure here is the same as the speed we measure here. It is the same of the speed of flow of charge here, all parts in the circuit, because there's only one pathway. If there were more than one pathway, then some electrons could go faster than others. And that's what we're going to get to next. I'm going to rebuild this. I'm going to pause the video, rebuild this as a parallel circuit in parallel to the battery. This is one pathway. If the electrons are leaving the battery, they can only go along one pathway to get back to the battery. Therefore, it's a series orientation. All of these elements are aligned in series. Okay? This light bulb is oriented in series to this one. What does that mean? That means that if I'm passing electrons through this light bulb, they have to go through this light bulb to get back around through the circuit. Okay? That's parallel. Okay? Or I'm sorry, that's series. Parallel orientation is the electron has a choice. It can go this way, it can go along path A, or along path B, or along path C. It's got options within the circuit. to get back to the battery. Okay, and let me pause the video and I'll set up a parallel circuit for you. Alright guys, so now I have a parallel circuit built here. I'll walk you through it real quick. And I noticed in review of the series circuit that the switch was cut off and didn't get a chance to see it. So that's basically the same way it was on the parallel circuit, or on the series circuit rather. The battery's in the same place as it was. What's really changed is the orientation of the lights to each other and to the battery. You can imagine, and even better if I do it this way, starting to look like a ladder, isn't it? So I've got a rung of a ladder here with a circuit element across the ladder, the two rungs of the ladder, and then I got another circuit element representing an additional rung. And I could change this battery, so rather than here, I could extend this and then put the battery in a bridge across this over to the switch, and then the battery would also be in a parallel orientation. As it is, the battery is in parallel to the circuit. I can also tell individually that the relationship between these two is parallel, and the relationship between the battery and the elements is parallel. And the way that I can do that, I can tell this element is wired in parallel to the rest of the circuit, because when the electron arrives here, it has a choice. If the electron is ever presented with a choice, that's a parallel orientation. Remember, series orientation is a one-lane road. This is not a one-lane road. This is an intersection. The electron that arrives here can choose to go through this light bulb filament, or it can choose to go to the other light bulb. So it has a choice when it arrives here. Okay. This is also technically wired in parallel, because electrons that arrive here could have chosen this alternate pathway back here. So both of these are said to be wired in parallel. I know that seems like that top one, well, that seems like it's just by the time you get here, that's all only one path. Well, no, there's two pathways to get back to the battery. There's, starting out here, the electron can either cross here and come back, or it can cross up here and come back. So two pathways back to the battery, or two or more pathways back to the battery, that is parallel orientation. The rungs of the ladder geometric structure gives away that it's a parallel circuit. In a parallel circuit, what was constant in parallel? Go back to the slides, go back to your notes, go back to the Bichon chapter. He says that voltage is constant in parallel. So I'm going to start out measuring current at different places along here. I think I'll just break the connection here, and then I'll break the connection across, well, no, that didn't work too well. Break the connection here, and then maybe, well, no, that's a 6er. I'll get back to that. I'll start out measuring voltage first. So I'm going to measure the voltage across here, voltage across here, voltage across the battery, voltage across the switch, and see if I get any variation in voltage, or if the voltage is indeed constant. So let me set this down right about here so you guys can see that. And immediately you see again we've got one bright bulb, one dim bulb. Hopefully that's good and centered for you. Let me switch to voltage. And I know that my battery in theory is supplying 3 volts. So I'm doing a 10 volt maximum detection here. And I'm going to measure across the battery first. Ding! Right halfway between 2 and 4, which is 3 volts. That's exactly what I predict. I also predict that I'm going to get the same measurement right here at the first light bulb. 3 volts. And I don't know, the second light bulb is dimmer, but 3 volts. So the push is the same. What's different? Well, this dimmer bulb, what is causing light to emit from those filaments? It's thermionic emission. And we know from the previous video and from previous review, the discussion we just had, current is proportional to heat production. And we know that filaments glow because of this principle called thermionic emission. We will talk about thermionic emission a little bit later, but that's how a filament works. That's how it gives off light, is through buildup of heat. The material that the filament is made of heats up because of the current passing through it, and then the electrons that the material has in its orbital shells start to get excited because of all the heat generated, and so they go to an excited state and then they cascade back down. And when they cascade back down, they give off visible light. So we can tell that there is more current passing through this one than there is this one, simply by the change in luminous intensity of the two filaments. And I'm going to confirm that with a measure. Let me do just a quick measurement and see if I can get a decent measurement of the current across. It might be a flawed measurement. Let's see here. What does it say? That says off the scale. Okay, that's greater than 250 milliamperes. Okay, so what I want to do is remove that. Now let me measure it and see if it's any. No, still off the scale. So the current is beyond my ability to measure here. Okay, but even without the ability to measure, my voltmeter is limited to 250 milliamperes. So we've got greater than 250 milliamperes of flow here, and I can just tell by understanding how filaments work and understanding thermionic emission that I have even though I can't measure it, I have greater current running through this than I have through this. So what does that mean? The electron flow across this circuit element is faster than the electron flow across this circuit element. So the current is varied across the two circuit elements, but I just confirmed to you that the voltage, in fact, across both of those was 3 volts. So it's the same as the voltage being supplied by the battery. And let me just quick measure the voltage across the switch. Bang. Why did that not work? Am I at the right setting? I am at the right setting. What's going on there? Should be getting 3 volts. That's weird. Okay, here. Now I'm getting 3 volts. Okay. So I don't understand. Oh, again, my meter's offering too much resistance to get a measurement across the switch. I can do a measurement, kind of do a measurement from the battery to the switch here. Gah. Okay, black here, right there. Can do this measurement. 3 volts. Alright guys, so that's parallel versus series circuit. The thing to remember, again, there will be quiz questions. In a series circuit, current is constant. That is, the flow of electrons is constant because it's a one-lane road. There's only one pathway. In parallel circuits, voltage, that is the force, is distributed evenly throughout the circuit. The voltage here is 3, the voltage here is 3, the voltage here is 3. Remember, parallel is a geometric arrangement where the circuit looks like a ladder. Series is a geometric arrangement of the elements where there's only one pathway to get it from the power source all the way back around to the power source. So if there's more than one pathway, it's not series. It's parallel. Okay? Or some hybrid. We're not becoming electrical engineers, so we don't have to worry about hybrid geometric arrangements just yet. Okay? All right. That is electrodynamics. I'll publish these videos and get them out to you before the end of the week.